Welcome back to ECE 501B. Homework 5 is due in 8 days. Then homework 6 is due shortly thereafter because exam number 2 is in 2 weeks, I believe is the date for exam number 2. 2 weeks just to keep us all on the same page so that I am aware of what I have to have done in a couple of weeks. Today we are moving on into chapter 6, and I am entitling this lecture the Orthogonalization lecture. We're doing a lot with orthogonality, and as we've learned in the past, orthogonality depends on what happening. Or how do we define something being orthogonal, and what are we talking about when we say things are orthogonal? What are those things? Vectors. So maybe that was too vague of a question, but we need 2 vectors, and vectors can be in quotes. And now what we mean by orthogonality is their inner product is 0, and so this orthogonality is going to depend critically on what we define as the inner product. And this inner product of 2 vectors could be defined differently on the same vector space. Meaning you would have one inner product space because you've defined this inner product one way, and you would have another inner product space because you've defined an inner product another way. And you could be getting maybe similar results, but not the same results necessarily with the same numerical values, for example. We have now, this is our list in this orthogonality or orthogonalization lecture. We'll look at orthonormal expansion of vectors, which really means we can start adding on and on and on, and if we add on, we want to go in an orthogonal direction to what we already possess or have. We will then do that more mechanically with this Gram-Schmidt orthogonalization process. The proof of that being possible is a proof by construction, and if you then believe the proof, you've now constructed how you would perform this building up of an orthonormal basis through the Gram-Schmidt orthogonalization process. We'll then basically state 4 corollaries related to orthogonality, and we'll talk about orthogonal projections and Perp, orthogonal complements, or a perpendicular subspace to a subset, for example. And if that subset that we began with is actually a subspace, and we look at its orthogonal complement, those 2 could be used to form a direct sum decomposition of a vector space. And then we can talk about a projection operator that now projects us orthogonally down into an underlying vector space. Here is a recap of what we have talked about in previous meetings. Proposition 615 tells us if we have a list of vectors, and if that list of vectors is orthonormal, and we know what an orthonormal list means, that means that they are pairwise orthogonal, and the normal part means that they have a length based on our inner product definition. They have a length of 1. Then if we have represented some arbitrary vector v in our vector space capital V as a linear combination of those orthonormal vectors, then the norm squared of that vector V is found, or can be found, by simply taking the scalars in our linear combination of V, finding their absolute value, squaring that, and adding those up. And that's playing on this property of these vectors in this list being orthonormal. Corollary 616 says that every orthonormal list is linearly independent. And that just means that we're basically adding new information each time we have an addition to our list. An orthonormal basis. What do we mean by something being a basis? What have we defined that to be in the past? A basis. It has to span the vector space, and those vectors need to be linearly independent. Here we are simply specializing that to have those vectors being an orthonormal list of vectors. Question? What is your question? Now, an orthonormal list just means that we are scaling the vectors to have a length of 1. And did you say an orthogonal list? Yes, so you could have an orthogonal list of vectors, and that also is going to be linearly independent. It just won't have some of these nice properties that an orthonormal list has, just because we haven't scaled the vectors in the list. But a basis now just means that we are able to span the entire vector space with these orthonormal vectors to have an orthonormal basis. And this is sort of a restatement of that, or saying it a different way. If any orthonormal list in V that has so many vectors in it, and so many in this case means that we have that many that are the dimension of our vector space V, then that's an orthonormal basis. So any orthonormal list in our underlying vector space that has that many vectors in it, and that many means that many has to be the dimension of our vector space, that will then produce an orthonormal basis. Corollary 616 shows us that that orthonormal list will be linearly independent, and the definition of a basis really says if you have a bunch of linearly independent vectors and they span the space, that now is a basis. So that's now our thinking behind an orthonormal basis. And this is really just a consequence of all of that orthogonality and all of those vectors floating around. It's nice to have things that are orthonormal, and it's nice to have actually an orthonormal basis. That makes things nice in terms of manipulation and playing and construction. Let's now look at then a result that plays on this orthonormal basis. Let's say that we have a list if E sub 1, E sub 2, E sub m is in fact an orthonormal basis. That tells us that it has to be the right length or the right number of vectors in that list. If this set or this list is an orthonormal basis on V, then we can actually decompose or represent any vector V in the linear vector space capital V as some linear combination of those basis vectors, and the amount of each orthonormal basis that we use can be found by the inner product of this vector V with the particular basis vector that it's in the direction of. Meaning we can now decompose this as V E1 inner product. That gives us the amount of V in the direction of E1, so scale E1 by that amount. Then find the amount of V in the direction of E sub 2 and use that to scale E sub 2. And keep doing that. These inner products now allow us to figure out how much of V is in the direction of this orthonormal basis. Here, let's say this is now the final piece, which is V with respect to E sub m and E sub m. If we have an orthonormal basis labeled as E sub 1 through E sub m, we can say this, and if we know that, what else can we say? What does this look like based on earlier results? Now we need to find basically the magnitude of each of those coefficients, which are these inner products. If I now say, oh, just find V and E1's inner product, take the norm of that, or take the absolute value of that and square it. Add to that the coefficient or the weighting of the E2 vector, take its absolute value and square that. And this parameterization and norm property is true for every vector V, little v, in the vector space capital V. And we can convince ourselves of that theorem. Let's now just write a general expression for V. Let's say V is now some A1 E1 plus A sub 2 E sub 2 plus A sub m E sub m. So we've now determined that V can be written as this linear combination, and we've now found these coefficients, A1 through A sub n. That's how V is now defined. What we want to do now is show that those coefficients are in fact the inner products. First, let's form the inner product of this vector V with E1. If we do that, we now have V E1 is this A1 E1 plus A sub 2 E sub 2 plus A sub m E sub m, inner product with E1. But now we can start to apply the additivity of our first slot property of inner products. Meaning we can now separate this into M inner products. We have A1 E1 E1 plus A sub 2 E sub 2 E1, etc., down to A sub m E sub m E1. The homogeneity of our first slot allows us to slide those scalars outside the inner product. We now have A1 with scaling the inner product of E1 with itself, plus A sub 2, inner product of E2 with E1, and now we can use what we know about this orthonormal basis and what that means. An orthonormal basis says that each of these vectors are pairwise orthogonal. And the only time that you have a non-zero result is when you're taking the inner product of a vector with itself, of these basis vectors, meaning this first piece in this example where V is inner product with E1, the first inner product is 1, and all the others are in fact 0. Or we now know that the inner product of V with respect to E1 is that coefficient A1 that we had found, let's say, a second way of parameterizing that vector V. Meaning, if we want to find A1, we just form the inner product of V with E1. And this process can be repeated for all of the subsequent basis vectors. So repeat for all other vectors in the basis. Which now says that the inner product of V with E sub k is going to return what? If I inner product V with one of these basis vectors, and let's say it's the specific basis vector k, E sub k, what's going to be that inner product? A sub k. Which means that VE1 is A1. VE2 is A sub 2, etc. Or we can now say that we can rewrite V, in fact, the way that the theorem says we can, which is scale each of these basis vectors with the inner product of that vector with the basis vector itself. Question? So the question was summation notation, you mean to use it here? So the summation notation, you could use it here if you wanted to. It's just, I was writing it out so that we clearly see it and we don't get confused by the summation notation. But you could collapse this down and say, okay, let's take the sum of these inner products, V with E sub L, sum over L equal 1 to M, and multiply each of those inner products with E sub L. And that would be fine. Is that what you were asking? The other part of the theorem, since we know that V can be written as A1E1 plus A2E2 with A1, A2, and A sub M appropriately defined by these inner products, then we can write that second piece by the previous theorem, or the proposition 615. So the second half of this theorem which was theorem 617, follows directly from proposition 615. And if you wanted to start thinking about the next textbook, which I need to start making that available for this class, we can now actually think about some of these issues or properties in an infinite dimensional space. Note the connection to Fourier series. where now you are looking at finding, let's say, these coefficients, C sub n, that might weight these complex exponentials, where you are looking now at this integral from some t naught up to one period beyond t naught, f of t, e to the minus j n omega naught t dt. What is that beast, that integral? What's another way of thinking of that integral now as an inner product? This is now an inner product. We are now trying to expand f of t with this infinite sum of weighted exponentials. Our waveform or function is f of t. What is this object in our inner product? That's the other piece, which this is now our set of basis vectors, isn't it? And what's the length of this? That complex exponential has a magnitude of 1, so this is now an orthonormal basis vector in this inner product. That's just something to connect or to go in a different abstraction from what we've talked about with these finite dimensional vector spaces. So, yes, so I guess maybe what I'm maybe, how do I want to say this? Maybe you need to bring the scaling inside the integral to give you the length that you need, but the idea is there as far as pulling that out. And we typically put that distance or the length of our time interval, if this is time, then we usually have that out front of our integral. Okay. Now, let's think about how we might build these orthonormal basis vectors. All of this is fine or okay. Somebody could, well, we could maybe get multiple orthonormal bases, so let's now make that plural. So these orthonormal bases are useful, or maybe even very useful, to whatever it is that we're working on. But now you might be wondering, how do we find it? But how do we go about finding them or producing them? And that's where Gram-Schmidt comes in. Here is now our Gram-Schmidt orthogonalization. Suppose now if V1 V sub 2 up to V sub m is a linearly independent list of vectors in our vector space capital V. Little v sub 1 through little v sub m haven't been normalized. It's just a linearly independent list of vectors. That's all we're saying right now. And we have m of those. then there exists an orthonormal list. Let's call those E sub 1, E sub 2, up to E sub m, where these lists actually span the same vector space or subspace in our vector space, with the span of v1, v2, v sub m equaling the span of e1, e2, e sub m, for j equaling 1, 2, up to n. If little m is 1, then you're building, or you're saying that the span of E sub 1, the orthonormal basis vector, is the same. It's in the same direction as V1. And now you are just normalizing V1 to have a length of 1. So let's now show that this can be done. And this will actually give us a way of generating these E sub 1, E sub 2, this list of orthonormal vectors. Let V sub 1, V sub 2, up to V sub m be linearly independent, be a linearly independent list in our vector space V. And now we're sort of going to do this construction by induction. So let's look at our base case. Whoops, let me just say, we'll do this with L. L equal 1. So now let's let E1 equal V1 over the norm of V1. And in this base case, do we have what we claim to have? What's the span of E1? Is that the same as the span of V1? And we just have V1 being scaled by some number, which in this case it's a particular value of a scaling, but it's in the same direction as E1, so the span of E1 is the same as the span of V1. And if you wanted to compute, you could see that E1 has a norm of 1. If you find E1 inner product with itself, you'll find that that now gives you a value of 1. So now let's continue with by induction. That means we need to assume that this is true for a particular value of L, let's say J. So assume now that J is bigger than 1, and E1, E2, E sub j, let's just say j minus 1. So this is the inductive step, has been found. So that span of V1, V2, V sub j minus 1 is equal to the span of E1, E2, E sub j minus 1. Now let's create the next step in this process, or the next piece of this creation of E1, and we'll actually do that in 2 steps. First, let's just find an intermediate vector W. Let's call that W sub j. So that now we have V sub j, and we want to take away from that pieces of our earlier basis vectors. Meaning, let's take away from V sub j the component of V sub j in the direction of E1. We take the inner product of V sub j with E1 and use that to scale E1 and remove that from V sub j. Now let's take the component of V sub j in the direction of E sub 2 and remove that from V sub j. And let's just keep going and remove V sub j minus 1. Whoops. The component of V sub j in the direction of E sub j minus 1 from V sub j. What we're doing is we're actually just subtracting or removing. This subtracts off all parts of V sub j that are along the different orthonormal basis directions. And these E sub L's are coming from our list, not all of them, up to the j minus first piece. Again, this is sort of step J. And something must be left from this process because V sub j was a list of independent, linearly independent vectors. So we are removing up to j minus 1 directions from V sub j, and now we have something left after subtracting off j minus 1 pieces from V sub j. Something must be left from this subtraction, since V sub j's, or maybe I should just say in general V sub i's, have been assumed to be linearly independent. And what's left, which we could refer to as the remainder, that remainder is actually perpendicular to all the E sub i's that belong to E1, E2, E sub j minus 1. So that's now W sub j. But we're not, that started with a V sub j, which wasn't any particular length. It was just some linearly independent vector, and it was linearly independent from V1, V2 up to V sub j minus 1. So now we need to make sure that the length of this new vector that we've created, this W sub j, we've removed from V sub j all the pieces that are in line with the earlier orthonormal basis vectors, E1 through E sub j minus 1, so that now we have to do step 2. Then let E sub j actually be W sub j normalized by its norm, or scaled by its norm. This E sub j is in the same direction as W sub j, and it's perpendicular to the preceding E sub j's, but now it has a norm of 1. And if we combine or remember what we've done, we've removed all of the pieces from earlier directions. We've now normalized that. Those two taken together allow us to say that V sub j is now in the span of E1, E2, E sub j. Which now says that that span is contained in the span of E1, E2 up to E sub j. And both of those lists are linearly independent. Both lists have the same number of vectors in them, and so those subspaces are actually the same. Let me try to write that down. So both lists are linearly independent. Both lists have dimension j, and therefore the subspaces defined by those lists are the same. So that now those spanning the same, they have the same, or now E's are orthonormal, and now we've created this orthonormal basis, or I'm sorry, an orthonormal list of vectors from a linearly independent list of vectors. So all we have to do is start throwing together linearly independent vectors. We can then use our inner product to make those now an orthonormal list of vectors in our particular vector space. And this is actually a very powerful result. The nice thing, too, is that we showed, or we created that proof by construction, which now allows us to build up from any linearly independent list an orthonormal list of basis vectors, or I'm sorry, of vectors. Meaning we not only know that it's possible to build up this orthonormal list, but we know how to build it now. We not only know it's possible, we know how to construct the orthonormal basis. Since we're dealing with a finite dimensional space, eventually that's going to terminate, and we're going to have our full number of vectors that we need to form a basis. We can now pull from that some nice corollaries, a number of useful results are possible. And I'll refer you to the book for the details, but let's just state some of these. Corollary 24 in chapter 6 says every FDIPS what in the world? Fire department is a police station? What? Every finite dimensional inner product space. Finite dimensional inner product space. Every finite dimensional inner product space has an orthonormal basis. That's nice to know. So you give or produce an inner product space that's finite dimensional, you can actually produce an orthonormal basis for that inner product space. Corollary 625. Every orthonormal list in a vector space V can be extended to an orthonormal basis on V. Is it clear what that is trying to say? Now you don't necessarily have to have a complete list to begin with. You just need an orthonormal list. Maybe your vector space is 10-dimensional. And maybe you have an orthonormal list that's 6 in length. How do you create a basis? Says we can do it. So now what we have to do, we want to get to 10 vectors, don't we? 10 orthonormal vectors that would form a basis, and we only have 6. So now we just have to start throwing some vectors in the set that are what? Linearly independent. So now you just have to sort of go in a slightly different direction, and then you can use Gram-Schmidt to orthonormalize that new vector that you've thrown into the pot. So you throw a vector in, number 7, and it's actually linearly independent. Okay, perform a Gram-Schmidt, and now you've created E sub 7. You need some more. Throw another one in. Make sure or check if it's linearly independent. Now you can continue. Gram-Schmidt that. Now you have 8. You need 2 more. Just keep adding in a linearly independent direction or manner, and then you can extend this original list to form an orthonormal basis. That's the idea. So now there can be, yes, because somebody could basically start throwing different linearly independent vectors for 7, 8, 9, and 10 and put you in a slightly different sort of direction orthogonal to the original 6 and then build from there. So you can have different, and that's why somewhere I had this, who knows where I had it, but I thought, oh, was it after that? No. Anyway, it was where I was referring to a basis, B-A-S-E-S. So you have multiple orthonormal bases possible. So the plural, instead of a orthonormal basis, I don't know if you can hear that difference, but one is a one and another is a collection of such, the plural. All right, so that's a way to create an orthonormal basis if you don't have the entire vector space spanned initially. Corollary 27. Suppose we're given T LV. What's that? What's that saying? So now T is a linear operator on a vector space V, isn't it? If that linear operator T has an UT, upper triangular representation, getting lazy, aren't I? If T has an upper triangular representation with respect to some basis, then that same linear operator T has an upper triangular representation with respect to an orthonormal basis on V. Meaning if you can create an upper triangular matrix with some basis, then you can actually create an orthonormal basis that will preserve that upper triangular structure associated with that linear operator T. And that's just applying Gram-Schmidt. Orthonormal basis is just Gram-Schmidt on the original basis. So you pick one of the vectors and you normalize it. Then you just start removing pieces in order to create an orthonormal basis from the original basis vectors. And you preserve the upper triangular structure of that linear operator. Corollary 28. given V, a FDCIPS, here the only thing we've added in from before is the C, and that's just complex. So we now have a finite dimensional complex inner product space, and that's easier to play with, we've learned. So given a vector space, or given V a finite dimensional complex inner product space, and a linear operator T on that finite dimensional complex inner product space, then T, that linear operator, has an upper triangular representation with respect to some orthonormal basis. And that's playing on this fact that this finite dimensional complex vector space allowed us to do this. Now we know that if we could, we can get an upper triangular matrix from a linear operator in a complex vector space, finite dimensional complex vector space, and once we have an upper triangular matrix, we can generate an orthonormal basis that will preserve that upper triangular structure. Let's now use some of these orthogonality concepts to now talk about orthogonal projection. Suppose somebody gives you a U, which is it's just a subset. It's not necessarily a subspace of a linear vector space V. If we're given such a U, a subset, we can define the orthogonal complement of that subset, U. And we will actually give that particular orthogonal complement a certain notation. We'll say U perp. Well, U with a perpendicular superscript. Called U perp, which is short for U perpendicular. U perp is the set of all vectors in the vector space V that are orthogonal to all vectors in possibly a subset. That subset might be a subspace. We'll make that distinction when we want to. But right now, U could just be a subset. Doesn't have to be a subspace. And what's a subset of something? Let's say a subset of the real line that's not a subspace. Do you remember some examples? We could have just some integer values on the real line, couldn't we? We could have the natural numbers, 0, 1, 2, 3. That doesn't form a subspace, but it's a subset of the real line. And that could be U. Maybe some vectors with those coordinates. Here is another notation. U perp is now the set of vectors V in the vector space capital V such that V with U, the inner product, is 0 for all vectors U belonging to the subset capital U. That's what we mean by U perp, capital U perp. And probably the textbook and others might say it's obvious that U perp is a subspace, even when U is a subset. Should be obvious. That U perp is a subspace even when U is not. Meaning U can be, it could be a subspace, but U in general is a subset, not necessarily a subspace. What does it take for a subset to be a subspace? So if U perp is supposed to be a subspace, what properties or characteristics or what do we need to show is true with U perp? Okay, it has to have closed under addition. That subspace, if it is a subspace, U perp needs to be closed under addition, has to be closed under scalar multiplication, and it needs to contain the 0 vector, doesn't it? If that's true, then U perp is indeed a subspace. So let's see if we can sort of explain that just with some wording. The only part of our vector space V that isn't in U perp are those vectors that are perpendicular to all vectors in U perp. That's kind of wordy, isn't it? So the only part of the vector space V that isn't in U perp are those vectors that are perpendicular to vectors in U perp. That's by definition of U perp. And we can't get to those vectors that are perpendicular to U perp. So if we're in U perp, we can't get to those vectors that are outside of U perp by playing with everything that's in U perp. Does that make sense? So we can't get to them, meaning the vectors that are outside of U perp, the vectors in V minus U perp, through addition or scalar multiplication of the vectors in U perp. So if that's the case, we can't get there. We can't get outside of this subset. We can actually say then that these vectors in U perp are closed under arbitrary linear combinations, and that includes then scalar multiples and addition. That's implying then that U perp is closed under arbitrary linear combinations. So that takes care of the closed behavior of U perp under addition and closed under scalar multiplication. We combine those by saying closed under arbitrary linear combinations. That takes care of both of the closed pieces. And remember how we defined U perp. We needed vectors V in our vector space to be orthogonal or have an inner product that's equal to 0. And what's a V that will allow that to happen? Well, the 0 element is orthogonal to every vector U, so we know that the 0 vector in V belongs to U perp, or 0 is perpendicular to everything so we do have the 0 element, so 0 element is in U perp. So even though U is a subset, U perp is a subspace. Its orthogonal complement is a subspace. So even though maybe we are just including these natural numbers on the x-axis, we can have if we were in R2, the y-axis would be U perp, so to speak. And that does form a subspace. Now, if we go ahead and allow U to actually be a subspace, then that allows us to decompose the vector space into two parts, and that's theorem 29. If U was actually a subspace, then the vector space V can be a direct sum decomposition of U and U perp. Another interesting corollary to that theorem, which is up to corollary 633, or equation 33, or it's labeled 33 in the textbook. If U is a subspace, then U itself is the perp of U perp. Meaning if we start, well, let me just go through some examples. But you can take the orthogonal complement of U, take the orthogonal complement of the orthogonal complement, and you'll get back to U. Here's sort of the example that I was just referring to before. Suppose that our vector space is indeed R2. And suppose we let U be the x-axis. Is U a subspace? Yes. So now what's U perp? That's the y-axis. Because we need everything in U perp to be orthogonal to everything in U. And I hope then that it's clear that we can span or produce the vector space V by the orthogonal complement, the direct sum decomposition of U with U perp. And this direct sum decomposition says we have a unique decomposition of any vector. We can write it as a vector from U and a vector in U perp. That's this direct sum decomposition idea or concept. What else do we know? If we look at U, the x-axis, we take the orthogonal complement to that, the y-axis, take the orthogonal complement of the y, we get back to x. So U is the orthogonal complement of its perp in this example. What about a second example? Suppose that V again is R2, but suppose that U is just this vector, 3, 0. It's not the real line, it's just a vector, 3, 0. So we're not saying that U is the span of 3, 0. We're just saying it's a subset of the x-axis. Then what do we know about U perp? It's now still the y-axis, isn't it? Because it has to be orthogonal. Every vector in U perp needs to be orthogonal to 3, 0. And the only way to do that is to have U perp being the y-axis. Can't have any component in the x direction. But hopefully it's clear that V is not the direct sum decomposition of that vector 3, 0 with the y-axis. You can't get to every point in R2 by taking anything in the y direction and just allowing to go over 3 units in the x direction. And we can see that U is not U perp perp. Because what is U perp perp? The x-axis, and that's not equal to this one vector or point 3, 0. Can we say what? I didn't hear your repeat of the perp. So I just heard, is it always contained in U perp, and I didn't hear the second perp the first time. So I'm glad I had you. So the question was, is U contained in U perp perp. Is that what I heard? And I think that's true, yes. But we are just really worried more about it's not equal to, because it's not. Okay? Now, we can now basically, let's just sort of talk about what we now feel maybe comfortable with in the case where U is a subspace the direct sum representation of V implies there is a unique decomposition of all vectors in V in terms of elements in these orthogonal subspaces. Meaning, for all U or let me change that. Let me say for all V in our vector space V, we can rewrite or decompose V into two pieces, U plus W, where U is in U and W is in its perp. And this now allows us to define an orthogonal projection, or I'm sorry, a projection operator. So we use this fact, this direct sum decomposition of a vector V, we use this to define a projection operator. Let's say capital P subscript U. Where this now represents the orthogonal projection of V, anything in V onto U. So we start with any vector V and we want to orthogonally, or we start with a vector in the subspace or the vector space V, and now we can decompose that vector into a part that's in U and a part that's in its perp. And now what we want to do is we want to project that vector orthogonally into the subspace U. And we'll do that by basically throwing away the component of V that's in U perp. So that's this projection operator. For all V in the vector space V, we can now say V is U plus W, where U is in big U and W is in U perp. If we've now done this decomposition of the vector v into u and w, then we can define this projection operator of pu operating on v to simply be u. Or, like I said, we're sort of throwing away the w piece. There are some properties of this projection operator. Pu is a linear operator, and some of its properties are that the range of this projection operator is all of u. The null space of this projection operator are all the vectors in u perp. Those will throw us into the 0 vector. If we have v and we take away the piece of v in u, or the projection of v into u, where is that going to leave us? So v we've now decomposed into u plus w. P sub u of v is just u. So we have u plus w minus u. We have w, and w lived where? In u perp. So this is now an element of u perp. So that was just w. Another result is that if we operate on it twice, how does that change p? P sub u. That's the same actually as p sub u. If we go into u and we try to project onto u again, we're back in u still. And if we look at the norm of pu, that's less than the norm, the norm of p sub u applied to v is going to be less than or equal to the norm of v for all v. And I may add just a little bit more after. I apologize, we've gone a little bit beyond time. And look at equation 35. I'll try to add that to the bottom of this, but it's really how you can create this projection operator out of an orthonormal basis.